You've mastered nuclear physics. You've nailed electromagnetism. But guess what? None of that matters if you're throwing away easy marks on the very first page of your Cambridge IGCSE Physics 0625 exam. Today, we're rescuing those foundational measurement marks before it's too late.
Imagine the exam timer ticking down. You've got exactly 5 minutes left. The invigilator is pacing the aisles. You're staring at a basic measurement data table, trying to calculate density, and suddenly you freeze. Your heart rate spikes. You are absolutely terrified of losing those precious grade boundary points to a silly, totally avoidable mistake. Sound familiar? Well, this explainer is going to show you exactly how to bulletproof your answers under that exact high-stakes pressure.
Now, measuring length, time, volume, and density, it seems so basic, right? I mean, it's literally chapter 1 of your coursebook. But here's the thing. This is exactly where foundational marks are won or lost. Every single year, examiners report that top-tier students bleed marks here simply because they don't know what the mark scheme is actually hunting for. It is incredibly common and honestly heartbreaking to see a student who perfectly understands thermal capacity lose their A-star just because they didn't correctly read a micrometer screw gauge or convert their standard units. So, let's talk about where these marks actually vanish. Ordinary revision completely fails because it ignores these painful common mistakes. We're talking about missing standard units on final answers, rounding numbers way too early in multi-step calculations, or just giving vague, non-scientific explanations. Take graph axis scaling errors, for example. Examiners literally pull their hair out when a student chooses an awkward scale, like say 3 units per 2 large squares on graph paper. It makes plotting the points accurately an absolute nightmare under exam pressure. And one bad scale decision? Boom! You lose the axis mark, the plotting mark, and the gradient mark all in one go. This really illustrates the before and after shock. On the left, we've got a typical flawed student answer describing an experiment. The volume is 45, and it goes up, so density is good. Yeah, that gets maybe a 2 out of 10. It lacks units, it lacks precision, and it completely lacks any scientific method. Now look at the top band examiner-approved answer on the right. V equals 45 centimeters cubed, calculated using the displacement method. Do you see that immense difference? It explicitly uses standard units and states the exact scientific method required by the syllabus. We're going to teach you how to write that right side answer every single time you put pen to paper.
To bridge that massive gap between a failing grade and top marks, you need this quick win framework. It's totally foolproof. Step 1 is concept. State the key definition, law, or equation right out of the gate. Step 2 is evidence or data. Pull the exact substituted values from your data table. Step 3 is scientific reasoning. Logically connect your specific data to the physics concept. And finally, step 4 is examiner wording. Package that entire thought into the precise terminology the grader needs to tick their box.
In just a moment, I'll show you the exact examiner clue that flips a weak, vague answer into the top mark band completely. It's a phrase they hunt for every single year. But first, you really need the framework that makes that clue completely obvious. Because look, if you skip steps 1 and 2 and just rush straight to the conclusion, that final clue won't save your grade. All right, let's dive into steps 1 and 2, concept and evidence, grounding your answer. Okay, I want you to actively engage with this one. Pause and predict. Imagine a student measuring the volume of an irregularly shaped liquid to calculate density. They find a mass of 50 grams, a volume of 21.4 cubic centimeters, divide the two on their calculator, and enthusiastically write down their final finding on the answer line. Can you spot the fatal error they are about to make before they even lift their pen? Let's review it. On the left, the student just dumped a raw, unedited number straight from their calculator display, 2.3333. They completely ignored significant figures and the standard units required by the mark scheme. Writing down 4 decimal places implies a level of precision that a standard school measuring cylinder absolutely cannot provide. That black space on the right? That's exactly where the examiner's red pen comes out. You simply cannot leave a naked number in physics.
So, how do we apply the examiner's fix? A top band answer has to include clearly substituted values into your density equation. You must state standard units, like cubic centimeters for volume, or grams per cubic centimeter for density. Always double-check your graph scales and uncertainty ranges, and above all, consider the reasonableness of your data. If your calculation says a small wooden block sitting on your desk weighs 4,000 kilograms, don't just box that answer and move on. You've inverted an equation or messed up a metric conversion. Stop, look at it, and fix it.
Moving on to step 3, scientific reasoning, connecting data to the laws of physics. Whenever you're asked to evaluate a practical investigation, like in Paper 6, you absolutely must bulletproof your answer. Identify the correct independent and dependent variables. Use correct physics terminology to describe apparatus features or anomalies. Justify the reliability of your measurements. And, this is huge, suggest specific, valid, practical improvements. Writing, "do it carefully" or "make sure you don't mess up" is never, ever a valid improvement. A valid improvement is suggesting insulating a beaker to reduce heat loss to the surroundings, or repeating a reading 3 times and taking an average to spot anomalies.
And finally, Step 4. Examiner wording. Fulfilling the command words.
Here's the crucial point. Your physics knowledge means absolutely nothing if you don't package it in the exact exam-safe wording the grader's hunting for. Look at this comparison. The vague student answer on the left says, "Make sure the ruler is straight," 0 marks. But the exam-safe wording on the right, "Avoid parallax error by viewing the scale at eye level," perfectly addresses the practical check for measuring length. Parallax error happens when your line of sight isn't directly perpendicular to the measurement scale, so that gap creates a false reading. Parallax error is that exact examiner clue I promised you earlier. Using that specific terminology changes the grade of your answer completely.
By mastering these common mistakes found right at the start of your textbook, measuring time, taking gradients, reading scales without parallax error, you lock in the foundational marks that protect your entire grade boundary. Before we move on, think about checking for 0 error on a micrometer screw gauge. If the jaws are closed and it reads 0.02 millimeters instead of 0, and you forget to subtract that from your final reading, your entire data table is corrupted. Identifying that one little foundational error builds an unbreakable foundation for the rest of your 0625 syllabus.
So, we've solved the measurement problem, and you now have the robust 4-step framework. But here's the catch. Your new top-band answer completely depends on understanding the specific command words Cambridge uses to test these concepts. If you don't know the critical difference between describe and explain when evaluating a practical setup, or how to manage your time across a demanding paper, this framework alone won't save you from running out of minutes on the clock.
Which is exactly why you need a strict time control system. And that's what we unpack in our next explainer. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations, and I'll see you in the next explainer to master those command words and implement a true time control system so you never, ever run out of time again. So what easily avoidable mistakes are you going to stop making today?